Assalamu alaikum. Can you hear me? Can you hear my voice? What about others? What about others? Can you hear me? Okay, so let's start our virtual session. This is 8th week virtual session. We were doing revision in our face-to-face lecture. So in continuation to that, we will discuss about transmission media today. As you know that transmission media are located below the physical layer and they are directly controlled by the physical layer. So we can say that transmission media belong to layer 0. Now, if you see this diagram, it will be clear to you that below physical layer we have transmission media. So computers and other telecommunication devices, they use signals to represent data. And these signals are transmitted from one device to another in the form of electromagnetic energy, which is propagated through transmission media. So electromagnetic energy is basically combination of electric and magnetic fields which vibrate in relation to each other, which includes far radio waves, infrared light, visible light, ultraviolet light, and X-rays, gamma rays, cosmic rays, etc. So for the purpose of telecommunication, transmission media can be divided into two broad categories. We have first category, that is guided media. As you can see, it is also called wired media. And the second category is unguided media or the wireless media. Now, if you will see the guided media category, it includes twisted pair cable, which in turn is divided into two major parts, that is UTP, unshielded twisted pair, and STP, that is shielded twisted pair. And we have coaxial cable and fiber optic cable. And here we have radio waves, microwaves, and infrared waves. So these are the two categories. And in guided media, we have three categories. So as you can see, guided media is basically that media that provide a conduit from one device to another, and it includes twisted pair cable, coaxial cable, and fiber optic cable. So a signal traveling along any of these media is directed and contained by the physical limits of the medium. So twisted pair and coaxial cable are metallic copper conductors that accept and transport signals in the form of electric current. And fiber optic cable is a glass cable that accepts and transports signals in the form of light. So this is our twisted pair cable. As you can see, we have two conductors, and these conductors are made up of copper, each with its own plastic insulation. They are twisted together as shown here. So one of the wires is used to carry signals to the receiver, and the other is used only as a ground reference. So the receiver uses the difference between the two levels. So in addition to the signal sent by the sender on one of the wires, interference, that is noise, and crosstalk may affect both wires, and it creates unwanted signals. So the receiver at the end operates only on the difference between these unwanted signals. So this means that if the two wires are affected by noise or crosstalk, the receiver is immune, that is, the difference is 0. as you can see over here, that we don't have parallel wires, we have twisted wires. So the reason is, if the two wires are parallel, the effect of unwanted signals is not the same in both wires because they are at different locations relative to the noise or crosstalk sources. Example, one is closer and another is farther. So this results in a difference at the receiver. So by twisting the pairs, a balance is maintained. For example, suppose in one twist, one wire is closer to the noise and others is farther. So in the next twist, the reverse is true. So twisting makes it probable that both wires are equally affected by external influences, that is noise and crosstalk. So this means that the receiver, which calculates the difference between the two, receives no unwanted signals. So it is clear that the number of twists per unit of length determines the quality of the cable, and more twists means better quality. So you see here, what is the effect? Here the noise effect is 16 units, and here in this wire the noise effect is 12 units. As you can see, here we have 16 units and here we have 12 units. Now at the receiver, no, this is chapter number 7, transmission media. This is chapter number 7, and here the total effect is 16 minus 12, that is 4. Now when these wires are twisted, the resulting effect will be 0. So there will be no effect of noise. So more twists means more quality. As you can see over here, here we have 14 minus 14, that is 0. Now we have shielded twisted pair cable and unshielded twisted pair cable. As you know that in the most common twisted pair cable used in communication is the unshielded twisted pair. And in STP cable, we have a metal foil or braided mesh that covers and encases each pair of insulated wires, conductors. So metal casing improves the quality of cable by preventing the penetration of noise or crosstalk. So it is bulkier and more expensive. So 16 minus 12 is not effective as 14 minus 12. No, I mean to say, see here. I want to say that in case of twisted pair cable, the wires are twisted, right? It is twisted. So why we have twisted wires over here? Why don't we have parallel wires? We can have parallel wires also, like this. But why don't we have these parallel wires? The result is, see, the effect of noise. If we have parallel wires, the effect of noise will be different. Okay. Now in this case, what we have 16 units in this wire and the noise effect is 12 units. Noise, yes, noise. So the total effect at the receiver will be 16 minus 12, that is 4. So that means the receiver will be affected by noise. Now what about this? When the wires are twisted, then what happens? The total effect, as you can see over here, it's 14. So 14 minus 14 is 0. That means there is no effect of noise on receiver. That's why the twisted pair cables are twisted. So more number of twists means more quality. Now next we have coaxial cable, and it is also called coax. It carries signals of higher frequency ranges than the twisted pair cable because the two media are constructed differently. So instead of having two wires, it has a central core conductor. You see, we have a central core conductor which is enclosed in an insulated sheath, and it is again covered by outer conductor, that is shield. The outer metallic wrapping serves as a shield against noise, and as a second conductor it completes the circuit. So this outer conductor is also enclosed in an insulating sheath, and the whole cable is protected by a plastic cover. It is made up of glass or it is made up of plastic, and it transmits the signal in the form of light. Now here you can see we have bending of light ray diagram. Now here, if the angle of incidence, that is the angle the ray makes with the line perpendicular to the interface, is less than the critical angle, then the ray refracts and moves closer to the surface. And if the angle of incidence is equal to the critical angle, the light bends along the interface. So if the angle is greater than the critical angle, the ray reflects and travels again in the denser substance. So you can see that the critical angle is a property of the substance, and its value is different from one substance to another. So optical fibers use reflection to guide light through a channel. So a glass or plastic core is surrounded by a cladding. Now this is shown in this figure. It's not like blackboard slides. No, it's in blackboard. It's same as that of blackboard slides. So you see, we have a glass or plastic core, and it is surrounded by cladding, which is of less dense glass or plastic. Now the difference in density of the two materials must be such that a beam of light which is moving through the core is reflected off the cladding instead of being refracted into it. Now these are the propagation modes. We have two propagation modes, multi-mode and single mode. In multi-mode, we have step index and graded index. So what do we mean by multi-mode? It means that multiple beams from a light source move through the core in different paths. So in multi-mode step index fiber, the density of the core remains constant from the center to the edges, and a beam of light moves through this constant density in a straight line until it reaches the interface of the core and cladding. Now in this second case, graded index multimode. It decreases this distortion of the signal through the cable. So the term index means the index of refraction. Now here we see multimode step index, multimode graded index, and single mode. So single mode uses step index fiber and highly focused source of light that limits the beams to a small range of angles, all close to the horizontal. The single mode fiber is manufactured with a much smaller diameter than that of multi-mode fiber. So this decreases in density and it results in critical angle that is close enough to 90 degrees to make the propagation of beams almost horizontal. So in this case, the propagation of different beams is almost identical, and the delays are negligible. So all the beams arrive at the destination together and can be recombined with little distortion to the signal. Now this shows fiber construction. Here we have outer jacket, which is made up of PVC or Teflon. PVC is polyvinyl chloride. So this is a substance that you might have studied in physics, that we have a PVC, polyvinyl chloride, or Teflon. And inside this jacket, we have a Kevlar strands. These are the strands which are known as Kevlar strands to strengthen the cable. And Kevlar is a strong material which is used in the fabrication of bulletproof jackets. So below the Kevlar is another plastic which is a coating to cushion the fiber. So the fiber is at the center of the cable and it consists of cladding and core. Now, unguided media transport the electromagnetic waves without using a physical conductor. So this type of communication is wireless and signals are normally broadcast through air and is available to anyone who has a device which is capable of receiving them. Now, here you can see the electromagnetic spectrum for wireless communication. So from 3 kilohertz to 300 gigahertz, we have radio wave and microwave. And from 300 gigahertz to 400 terahertz, we have infrared. And from 400 terahertz to 900 terahertz, we have light waves. You can see over here, there is no difference between radio wave and microwave, but electromagnetic waves ranging in frequencies between 3 kilohertz to 1 gigahertz are normally called radio waves. So this is the difference. Although you cannot see the difference over here, but the waves which have frequencies between 3 kilohertz to 1 gigahertz, they are called as radio waves. And Waves which have frequencies between 1 gigahertz to 300 gigahertz, they are called microwaves. So the electromagnetic waves which have frequencies between 1 and 300 gigahertz are called microwaves, and microwaves are unidirectional. So when an antenna transmits the microwave, they can narrowly focused. This means that the sending and the receiving antennas should be aligned. So the unidirectional property has the advantage that a pair of antennas can be aligned without interfering with another pair of antennas. Then we have infrared. So here you can see those signals which have frequencies from 300 gigahertz to 400 terahertz. They are called as infrared based, and they can be used for short range communication. So infrared signals having high frequencies cannot penetrate walls. So this is an advantage, and this characteristic prevents the interference between one system and another. So a short range communication system in one room cannot be affected by another system in the next room. So we have infrared remote controls which do not interfere with the use of those remotes by our neighbors. Now next we have light wave. Light waves have frequencies from 400 terahertz to 900 terahertz. Now let's load the content of chapter number 9. This was all about chapter number 7, where we have discussed about transmission media. So here we can see the nodes and links. As we know that communication at the data link here is node to node. So a data unit from one point in the internet needs to pass through many networks, that is LANs and WANs, to reach another point. So these LANs and WANs are connected by routers, and it refers to the two hosts and the routers as nodes and the networks in between as links. So you can see over here, if we have any system or router, then it will be called as nodes. So we have node over here. And if we have any network in between, that will be called as link. Now we have point-to-point network, so this is a link. Again, a router, so this is a node. Then we have LAN, that is a network, so it is called as link. So the routers are called as nodes and the network in between are called as links. Here you can see that we have divided the data link layer into two sublayers. The one is called media access control and another is called data link control. So here in figure A, you can see data link layer of a broadcast link. So we have two sublayers, MAC and DLC. And in case of data link layer of point-to-point link, we have only DLC, not MAC. Now see this figure. Now in this figure, it shows IP addresses and link layer addresses in a small internet. So if it will be asked to draw this frame, will you be able to draw this? If we have one system whose network IP address is N1 and whose link layer address is L1, and we are to transfer the frame from this system to this router, okay, whose network address is N2 and the link layer address is L2, and it is asked to draw this frame, will you be able to draw this? Not all. Not all means it may be asked to, maybe, yes, maybe. It may be asked to draw the complete network, or it may be asked to draw this frame. Will you be able to draw it? Because in case of data link layer, you need, it's not hard. It's not hard. Remember that you have to show the data part, okay? Show the data part first of all. This is the data. First of all, you will show data. Then you have to show the network address. Now, what's the network address over here? We have N1, the IP address of the sender, and the IP address of the receiver. Where is the receiver? The final receiver. This is Alice. This is Bob. Alice and Bob. So we have the IP address of the sender and the IP address of the receiver. So what you will have? You will have N1 and, yes, Alice is the sender and Bob is the receiver. Yes, the last one. That is final receiver. See, who is the final receiver? These are the two systems, right? These are the two systems. This system and this system. These are the final systems. And in between what you have? You have routers in between. Okay, so don't get confused with this router. Now you are sending the frame from this sender to this receiver. And in between you have two routers. So whenever you are sending a frame, first of all, it will include the data. So we have data packet. Then the IP address of the sender and the IP address of the receiver. So IP address of the sender is N1 and IP address of the receiver is, the network address is N8. So we have N1, N8. Now find out the data link address. Find out the data link address. Now here in data link address, there's a mistake. There's a mistake. What is the link layer address of sender? Yes, it is L1. So this should be how much? This should be L1. Now next is, see the data link address of the router. What is the data link address of the router? It is L2. It is L2. So here it should be L2. Okay. So it will be L1, L2. L1, L2. Now see this frame. See this frame? Again, this frame will have data packet. So you have data over here. Then the network address of the sender and the receiver. So we have N1 and N8. Now we should have the link layer address. The link layer address of the routers. So here it should be L4 because here we have L4. You see, we have L4. Yes, between the routers. We will see the IP address of sender and receiver and the link layer address of the sender and the router. See, here the frame is between the sender and the router. Here the frame is between these two routers. Okay, these two routers. So we will see the link layer address. We will see the link layer address of these two routers. So you see we have L4 and then the link layer address of this router is L5. So we have L5. This is correct. This is absolutely correct. Now what about this? What about this? We have data. We have the IP address of sender and receiver, that is N1 and N8. Now what about this? It should be how much? It should be I will make corrections over here. Okay, I will erase all this and I will make corrections. You can note it down. I will remove all this. I will make correction. There's just one correction. Here it should be, instead of L7, it should be L1 and it should be L2. Okay. So instead of L7, it should be L1. Instead of L8, it should be L2. This is the correction over here. And here it should be L7 instead of L1 and it should be L8. This is the correction. Rest it's correct. So you have to make correction over here. Why not L5? Where is L5? See here, L5 is here. Okay, so that's why we have taken L5 here. But what about this? Okay, we are at this point. We are at this point. Okay, so here at this point, the link layer address is how much? It is L7, right? Here at this point, what is the link layer address? This is L7. So it should be L7. And what is the link layer address over here? This is L8. So it should be L8. Yes, if you have any doubt, you may ask. Now, we know that there are three types of addresses. Those addresses are unicast, multicast, and broadcast. Now, in case of unicast address, each host or each interface of a router is assigned a unicast address. Unicast means one-to-one communication. So a frame with a unicast address destination is destined only for one entity in the link. What about multicast? Some link layer protocols define multicast addresses. Multicasting means one-to-many communication. And then we have broadcast. Broadcast means one-to-all communication. So a frame with a destination broadcast address is sent to all the entities in the link. So if we have FF, what is this? This is a broadcast address. This is a broadcast address. Then we have address resolution protocol. This address resolution protocol is defined in the network layer. It belongs to the network layer, but we will discuss it here because it maps an IP address to a logical link address. So ARP accepts an IP address from the IP protocol. It maps the address to the corresponding link layer address and it passes it to the data link layer. So you can see over here that we have ARP in the network layer, but still we are discussing it in link layer address because it is close to link layer and it provides all the services that are required by the link layer. So here you can see the ARP operation. The ARP request is broadcast over here and the ARP reply is unicast. That means whenever a request is being sent, it is being sent to all the systems in the network. So you can see it is being sent over here also, and here also. So the request is broadcast. Now when the link layer address is matched, so this system will reply that yes, the link layer address is L2 and it's my address. So the reply will be only from system B. So in this sense, the reply is unicast, that is one-to-one. But here in this case, the reply is broadcast, that is one-to-many. Here we can see the ARP packet where we have destination protocol address, then destination hardware address which is 0, then source protocol address, source hardware address, we have hardware length which is from 0 to 8, then from 8 to 16 we have protocol length, and then from 16 to 31 we have operation. And here we have from 0 to 16 we have hardware type and 16 to 31 we have protocol type. Now see this media access control protocols. Here we have three categories. We have random access protocols, controlled access protocols, and channelization protocols. So in random access protocols, we have 4 protocols. One is missing, and that is Csma. It should be Csma also. So here we have 4 protocols, that is Aloha, Csma-CD, Csma-CA, and Csma. So these protocols are mostly used in LANs and WANs, local area networks and wide area networks. The next category is controlled access protocol. In this we have three protocols, that is reservation, polling, and token passing. So some of these protocols are used in local area network. And then we have third category, that is generalization protocol. So here we have three protocols, FDMA. FDMA stands for frequency division multiple access. Then we have TDMA, that is time division multiple access protocol, and CDMA, that is code division multiple access. So these protocols are used in cellular telephony. In this figure, you can see pure Aloha network. Here there are four stations, station 1, 2, 3, and 4. And these stations contend with each other for access to the shared medium or shared channel. So in this figure, you can see that each station sends 2 frames. So total, how many frames we have? Each station sends 2 frames. So total, there are 8 frames on the shared medium. So some of these frames collide because multiple frames are in contention for the shared channel. So this shows that only 2 frames survive, one from station 1 and one from station number 3. Here, the pure Aloha protocol relies on acknowledgement from the receiver. So when a station sends a frame, it expects the receiver to send an acknowledgement. And if the acknowledgement does not arrive after a timeout period, the station assumes that the frame or the acknowledgement has been destroyed, and then it will resend the frame. Now this is slotted Aloha network. In slotted Aloha, we divide the time into slots of TFR and forces the station to send only at the beginning of the time slot. So this shows an example of frame collision in slotted Aloha. So because a station is allowed to send only at the beginning of the synchronized time slot, so if a station misses this moment, it must wait until the beginning of the next time slot. So this means that the station which is started at the beginning of this slot has already finished sending its frame. Now we have CSMA. CSMA stands for Carrier Sense Multiple Access. It requires that each station first listens to the medium. That is, it should check the state of the medium before sending. So CSMA is based on the principle that sense before transmit or listen before talk. So CSMA can reduce the possibility of collision, but it cannot eliminate it. So the possibility of collision still exists because of propagation delay. That means when a station sends a frame, it still takes time for the first bit to reach every station and for every station to sense it. So we can say that a station may sense the medium and find it idle only because the first bit sent by another station has not been received yet. These are the three persistence methods: one persistence, non-persistent, and p-persistent. Now what happens in one persistent method? What in this method, the station will find, first of all, it will find the line idle. When it will find the line idle, it will send its frame immediately with a probability of 1. So this method has highest chance of collision because 2 or more stations may find the line idle and can send their frame immediately. Now what happens in non-persistent method? A station that has a frame to send senses the line. If the line is idle, it will send immediately. And if the line is not idle, it will wait for a random amount of time and then senses the line again. So the non-persistent approach reduces the chances of collision because it is unlikely that 2 or more stations will wait for same amount of time and retry to send simultaneously. Now we have p-persistence method, and this method is used if the channel has time slots with a slot duration equal to or greater than the maximum propagation time. So the p-persistent approach combines the advantage of one persistent and non-persistent approach. Then we have CSMA-CD, that is Carrier Sense Multiple Access with Collision Detection. In this method, a station monitors the medium after it sends a frame to see if the transmission was successful. And if so, the station is finished. And if there is a collision, the frame is sent again. And in Carrier Sense Multiple Access with Collision Avoidance, we have 3 strategies: the interframe space, the contention window, and the acknowledgement. Now we have reservation method. In reservation method, a station needs to make a reservation before sending the data. So time is divided into intervals, as you can see over here. And in each interval, a reservation frame precedes the data frame sent in that interval. And in polling method, one device is designated as a primary station and the other device is designated as secondary station. So all data exchange must be made through the primary device even when the destination is a secondary device. So the primary device controls the link and the secondary device follows its instructions. So you can see over here, we have select and poll functions in polling access method. So will you be able to draw this diagram if it will be asked to draw for select and poll function? What you will do, first of all, a cell, that is select frame, is sent, then an acknowledgement frame is sent, then the data frame, and again acknowledgement. Okay, so these are the 4 steps in select polling access method. What about poll? Polling access method, first of all, poll frame is sent, then NAK frame, then poll frame, then data frame, and then acknowledgement frame. So total 5 steps we have in polling access method, poll function of polling access method. Now in case of token passing, what we have? We have physical ring, we have dual ring, we have star ring, and we have bus ring. Questions can be in the form of true and false. True and false can be asked, or it may be in the form of multiple choice question. Okay, so the question can be asked in different ways. Maybe in the form of fill in the blanks, multiple choice, true and false, or a diagram can be given like this. Okay, you have to complete this diagram for select function and for poll function. So different questions can be asked in different ways. Then we have channelization. In channelization, we have FDMA, TDMA, and CDMA. That is frequency division multiple access, time division multiple access, and code division multiple access method. So with this, we came to an end. So no need to draw, just fill them. No, it depends. Maybe it may be asked to draw the complete diagram, or the diagram will be given to you partially. You have to fill it up. So it depends. So your exam is on 9th, I suppose. So you still have time. Just go through all the chapters thoroughly. If you have any doubt, you can mail me. I'm here to help you out. All the very best for your exam. We will meet inshallah after midterm exam. Till then, take care all of you. Assalamu alaikum.